looking at question 5 and also question 6, which for question 5 we know these are functions. We've learned this in high school. Also, we learned about them here, right? And then what we should be able to do in this case, we should be able to analyze rational functions or any kind of function that we're given, and also be able to evaluate specific integrals, right? So if you can check, question 5 was based on a rational function. It was based on a rational function where they said we must find the intercepts with the axis, meaning we should find the x-axis, y-axis. Also, the second one, they say we must find the turning point. And then the third one, they say we must find the intervals, or the interval where the function is increasing, and the intervals, or the intervals where the function is decreasing. And also we must find for concave down and also concave up, right? So B, let me go to B and see what B said. Yeah, B was just integration, and we say that 6.1 was there in, I think it's test 2 or 3. So this is repeating itself. So now when we come to the first problem, they say that we must find the intercepts with the axis. So first we're gonna look at the x-intercept. When we look for the x-intercept, remember, for x-intercept, y or f of x should be set to be 0, right? So it means that if I can set this thing to be 0, I can now solve for x. And in this case, how do we solve for x? We multiply both sides first by this denominator, so it can go, right? And then we focus on x minus 2, your x to the 2 minus 3, which is equal to 0. And if I make x with the formula here, I'm going to get that x is equal to plus or minus root of 3. And it means that our x-intercept are like this. This is our x-intercept, where y is equal to 0. And then we come now to look for the y-intercept, which we see that for the y-intercept we must set x to be 0. And then when we set x to be 0, we found that we get 3 over 4. And the y-intercept will be this, right? So now we see that finding the x-intercept and the y-intercept, I believe that everyone got that question, right? It was straightforward. Then we come to dealing with the turning points. So on this function, we're given that f of x is equal to x squared over your x squared minus 3 over 2x squared minus 4. So when we look at this question, I can decide, I get the question is like this, is saying f of x, which this is x squared minus 3 over 2x squared minus 4. I can decide to let the numerator be u and let the denominator be v. So I can have f of x is equal to this, right? To simplify things. This one usually simplifies things, right? Then what I do, I know that for me to use quotient rule, let's say we have this. Quotient rule says that f prime of x will be equal to, remember last time I said that you can just multiply by uv minus uv all over v squared. And we know that the numerator should be the one to have a prime first, right? So this will have a prime. And this u will have a prime. Then this side will have v having a prime. So what I need here, I just need to come here and solve and find u prime, which is this, find v prime, which is this, right? And also square the denominator. So you can also apply this for simplicity. This simplifies things. So since our u is, we know that the u is x squared minus 2, which is this. U is x squared minus 2, v is 2x minus 4. If I derive this, I'm going to get 2x. If I derive this, I'm going to get 4x. So those are our u prime and v prime. You see the formulas here. I've used the formula as it is. So What I do now next, I just come and plug, right? We know that u prime is 2x. I plug 2x on u prime. We know that v is this. We plug that. V prime is that. We plug 4x. And u is that. We plug u. And we square v there in the denominator. You see, right? So it's much simpler this way. So things can get simple like that. So now, since we remember, we use first derivative for turning points. We use first derivative to check our point. Then for the second derivative, we're gonna use it just to check. It's actually used to confirm, right, the turning point, if this is the other correct turning point or not. But now, remember the question said that for B we must find the turning points, right? Then for this, after simplifying the numerator, or when I simplify the numerator, this side, let me use this pen. This side, I simplify it here. I find that it's 4 to the 3, it's 4x to the 3 minus 8x. Then when I simplify this side, I find that it's this, right? So I simplified these separately so that because there wouldn't be space for me to put them all in all. So now since I've simplified it, now I subtract them according to the numerator. According to the numerator, they are subtracted. And then when I subtract them, I get 4x. You see right there, this one will cancel this. Then when these two subtract, we're going to get 4x. So it means that on the numerator now I have 4x. Then I'm going to let these two be equal to 0 for me to solve for x. You see right? Then I solve for my x. I find that, let's say I let this be equal to 0. I'll still multiply by this both sides, right? And then I'm left with 4x equals to 0, which implies that x is equal to 0 in this case. So from this case, we are going to use, remember I said that we're going to use the second derivative or the test point to confirm the turning point. So we're going to use the second derivative to confirm the turning point. So in other words, we are going to use the second derivative to check what type of a turning point is this. Is it the local minimum or the local maximum? You see right now. So here we found that x is 0. So since we found 0, so I'll just write my turning point here. We found that x is 0. To find y, I'm going to go back to the equation, right? And plug my 0. Remember when I plug 0, I get 3 over 4. It means that the turning point is 0, 3 over 4. So first prime is used, first principle is used to find the turning point, and then the second principle, we're going to use it to check whether it's a local minimum or local maximum. Then I use the second derivative now. This is the function. It means that I can let u be equal to 4x. I let v to be equal to this denominator. Then I find u prime and v prime. Remember how to derive this. We know, right? Here we first drop the 2. We keep this as it is, which is this. We subtract 1 here. We times by the derivative of the inside, which will give us 4x. Remember here, when I derive 2x squared minus 4, I'm going to get 4x. The derivative of the inside is 4x. You see, right? Then when I simplify this times this, I'm going to get 8x. Then when I factor out 2 inside, you see I factored out 2 there inside, right? Then the 2 will go out. 8 times 2 will give us 16. That's why there I wrote it in this way. You see, right? So if you see that there's a constant you can factor out inside, you can do that. You can factor out 2. So if I factor out 2 first, it will go out and be 4. So it will be like this in first, right? Then this times this will give us 16x. You see, right? Then from here, we see that I have all the things that I need. I have u prime, I have v prime, u prime, I have u, I have v. So I can go to the equation and plug. Then when I come to the equation, I'm going to plug and simplify this numerator, right? I can simplify that numerator. Let's see what I get when I simplify the numerator. Or if you want, you can still not simplify it, right? But you can simplify it if you want. Then if I multiply, but yeah, simplifying this numerator will take time. So that's why, yeah, there's no need to simplify it, right? If you see that it will take time, don't simplify it. I get here, I'm not forced to do this to find x here. I already have my x. X is equal to 0. So I'm going to use that x which I have. So now, when I plug the x here, I find that my value is greater than 0. That will be a local minimum. And if the value is less than 0, it will be a local maximum. It means that this turning point is in this manner. You see right now? So now that's the case. So we say that when we plug 0 there, we get 1/4. And 1/4 is greater than 0. So we're going to have a local minimum at 0, 3, 4. So next time they can ask you to say find the local minimum or local maximum. Right? They can say that find the local minimum, find the local maximum. So for you to do that, you see here they said find the turning points. You can use first principle, you find the turning points, but then you must know, is it a local minimum or local maximum? Is that right? So for you to check local minimum, local maximum, use second derivative, but plug in the x that you got from first derivative, right? So now since we see the turning point for this question, we come to check if it decreases or increases. You see, right? So for decreasing or increasing, in this case, we are also going to derive, since here we already found our first principle, right? We're going to use first principle to check if this is increasing or decreasing. You see, right? So we're going to check whether this is increasing or decreasing. So now let's check. Who can tell me when is this? I want to ask this, right? Is this increasing when f prime of x greater than 0 or increasing when f prime of x is less than 0? Which one is correct here? Who can tell us here? Who can tell us here? Is it increasing or decreasing when that is the case? Anyone? Guys? Who can tell us, is this increasing when we are having greater than 0, or is it increasing when we are having less than 0? Which one, guys, is correct? No. So no one is gonna answer, right? I can't see if you are answering on the comment sections. I can't see the comment section. Or let's keep the question, then we'll come back when one has the answer, right? So we come to concave up and concave down. So when we come to the concave up and concave down, this is like, it's similar to when you're finding the local minima or local maxima. Remember, for the concave up, concave down. You see right now. So concave down, concave up. So you remember, when you check in the local maxima or local minimum, you check with the second derivative. So also the concave up and concave down, you'll use the second derivative. The only difference is that you are going to test the signs. You see right now. We are going to test the signs, then we'll decide where do we have a local minimum and where do we have a local maximum. So as you can see here, for us, if we simplify the numerator, the test signs changes. For f, the second prime of x, this will be greater than 0 when the denominator is positive and the numerator is positive, right? And also approximately the concave upon this, excluding the asymptote. So when we exclude, who can tell me also what is the asymptote, guys, before we can discuss this question? You guys are quiet. It seems like if you don't reply, we're not gonna have a session, right? You must reply. I can't talk to myself. Or should we skip the questions, or guys, or should we end the session, since I've given you enough time to answer, but you guys don't want to communicate? And if you're not communicating, it's like I don't know if you're even listening, but then you are not saying anything. If that's the case, I'm also gonna leave this one, right, until someone is ready to say something. And then we come here. When we come to this one, so what I can say, right, go look at these. I really don't want to reply when I ask you questions. Go look at these 2 questions and see how can you go about them. So when we come to question 6, right, on question 6 for 6.1, this is simple because we're going to use u substitution for 6.1, right? So for 6.1, we're going to let the one in the numerator, the one in the root, to be u, the one inside the root. So we're going to say let u be equals to 2x minus 1, which is the one that is inside the root. So remember, for u substitution, we focus on 2 expressions. For u substitution, we are given 2 expressions. We are given 2 expressions. One, it should be simple to derive, and the other one should be difficult to derive. You see, right, ne? So the other one should be difficult to derive. So what we do here, we focus on the one that is difficult on u substitution. So between this one and this, we realize that the one with the root is the one which is difficult. So we're going to let that be u, the inside only. You see, right now, we let its inside be u. Then when we let this be u, we are going to derive it. When we derive both sides, we get du is equal to 2 dx, right? And again, when we come, remember, when we're coming to plug here, we're going to plug u here, right? And we plug du over 2. But this would be left out because we don't have that. So, but what we see that something is common here. It's 2x. So I can make 2x substitute the formula from this so that I can plug there. You see, right? And 2x, when we make it substitute the formula, we're going to get that 2x is equal to u plus 1. So when we get to u plus 1, we are going to plug there. When I plug u plus 1 into x, I'll get that 1 plus 3 is 4. So I'm going to get u plus 4. And then this one will be u. inside here, right? And our dx will be equals to du over 2. So and then I take out the 1 over 2 outside as a root. Then I change this to 1 over 2, the exponent 1 over 2, which is this. So I can multiply through, right? Like this, before I can integrate. So another thing, we are not allowed to write our integral like this. We are not allowed to write our integral like this. We are not allowed to do this. I know some can do it, right? But we are not allowed to write our integral like this. You see right now? You're not allowed to do something like this. You see? You can't do that. You're not allowed. So you must simplify that for you to integrate. So when we come to this case, we are going to just multiply through. When we multiply through, we are going to get this. When I multiply here, I'm going to keep the base at the exponent. The exponent of this one is 1. When I add 1 plus 1 over 2, I get 3 over 2. Then this one, it becomes that, right? Because there was a constant at first. So when I integrate, remember, I'm going to take this, add 1 on the exponent, then divide by that entire exponent. So these exponents should be the same. Then I do the same here. I add 1 there, which I'll get 3 over 2, divide by the entire exponent. Then this, for me to simplify it, I can just turn it, right? I can just flip it to get this. Also this one, I can just flip it to get this. So I'll get 2 over 3, and 2 times 4, we know that it's 8. All right. So this would be, this one, this integration is simple. With simplifying, you can simplify anyhow. It doesn't matter how you simplify, right? But then you should make sure that you're always fast when it comes to simplifying. Then you substitute back your u, right, at the end. Substitute back your u. And don't forget to add c. When all the integral signs are gone, you add c. All right. And some of you like to write the integral signs, then you don't write the du. You must make sure that you write that du. It should be written down. So now the solution will be in this case, because our u was 2x minus 1. So wherever we see u, we plug our 2x plus minus 1. That I'm sure that we know. We are certain that we know that. Then when we come to the third question, now we're given this. They say this is the integral of x to the 3 ln x. Then we're going to use Liat here. We agree, right? For this integral. This Liat says that we are going to let the first expression that comes first in Liat to be u. Then when we check this 2 here, we realize that this one, ln is log, right? It comes first. So we're going to let log be u. We let that be u. And then this one will be dv. You see, right? And then this one, we're going to derive it. We get 1 over x dx. And then we integrate this. We get x to the 4 over 4. Then we come back to the formula. The formula says that here we're going to have the integral of u dv, which is equals to uv minus the integral of v du, right? Which, when we plug, we know our u is ln x. So we plug ln x times v is this. We plug v minus v times 1 over x dx, which this is our du right now, which is this. We just plugged the u there. So when we simplify here, we're going to be left with x to the 3 inside here, right? We take out the 1 over 4 as a constant. We're left with x to the 3. Then we integrated the x to the 3 to be x to the 4 over 4. Then 4 times 4 will give us 16. That's why here we have 1 over 16. I'm sure we see that. Then don't forget, when all the integral signs are gone, you can now add c. That is what you must always keep in mind. So I believe that these ones are simple, right? That's straightforward. You can easily get them. So when you come to the third one, this one is partial fraction, right? And then when you come to this one, you must pay attention to rules. When we come to partial fraction, we have certain rules that we should look at. The first rule is that for you to apply partial fraction, the denominator should be factorizable. You see right now, you must be able to factorize the denominator. So if you're able to factorize the denominator, then that's a tick. You say right now, you know that the denominator, if the denominator can be factorized, therefore you can apply partial fraction. So already this denominator was factorized. Another thing, for you to apply partial fraction, this is the second thing, right? For you to apply the partial fraction, you must make sure that the degree of the denominator, or the exponent, the highest exponent of the denominator, is bigger than or equals to the highest exponent of the numerator. Let's say, for example, if the numerator is x squared, denominator is x3, you can apply partial fraction. It's right. Now I'm focusing only on the highest degrees. Then if the numerator is x squared, denominator is x squared, you can apply partial fraction. If the numerator is x squared and the denominator is x, you can't apply partial fraction. Reason means because the numerator has a higher degree than the denominator. The degree of the numerator in this case, it's 2. You see right now? And the degree of the denominator is 1. So you can't apply partial fraction here. You must apply long division first. If that's the case, we say right now. So now we come to this one. Let's check the highest degree of the denominator. The denominator, if we check first the expression, this one can give us x squared, right? We check the second one, gives us x. X times x squared, it's x to the 3. So the highest degree of the denominator is x3. So the highest degree of the numerator is x squared. So this is this case, right? The first case. And we can apply now partial fraction. So we can use partial fraction decomposition. So we can use it. Now, since we know the rules of using partial fraction decomposition, now we come to knowing how do we apply it. Now the question is, how do you apply partial fraction decomposition? So with partial fraction decomposition, let's say this was not there. This 2, let's say this 2 was not there. We had x plus 1, x plus 2. We're just going to have this 2. You see right now? We were just going to have those 2. You see? We're just going to, so what we do, we forget about the numerator. We expanded this. We separate this 2 and put the plus in between. Then here we put a. It's like we put the plus in between. We put b, right? Like this. So as long as this is x, not x squared, as long as this is x, you see right now, to the degree 1. Then, the moment this now has a squared, we should start from exponent 1, exponent 2, then we stop. You see, this one started from exponent 1 to exponent 2. You see right now. Then, if this had 3, it means that I was going to also start from 1 up until 2 till 3. dx plus 1. So if you feel lost here, it means that you didn't do your homework well right now, because these things are there on the guide. So if you feel like maybe you're lost there, it means that you must go to the guide after the session. Then you look at the notes based on this. You focus on the notes based on this. Then you'll be good to go, right? Also on the previous ones, because no one was answering on the previous ones. So it means that you guys need to do some self-introspection. So now, if this was ending at 3, I was going to start from 1, 2 until 3. You say right. So in this case, that's why we are starting from 1 up until 2, because there it ends at 2. So we know that now. We do understand why are we having 2 here up until 2. Why are we having this 2? Someone would not put this one. They would just put 1, 2. You see right? So now you know why am I having that. So now from here, I'll multiply both sides by this denominator. So this denominator, when it comes here, this is going to cancel. This will be left with the x plus 1 all squared. When it comes here, one of these will go. We'll be left with this. So right, when it comes here, this one will go. We'll be left with x plus 2. This is the fastest way to simplify, right? Simplifying, you can simplify anyhow, it doesn't matter. So this is not my concern here. But we check something here. This denominator, let's say I equate this denominator to 0. Yes, right. Or not entirely, but even when I equate this denominator to 0, I'm going to get that x is equal to -1 or x is equal to -2. You see right now, x will be equal to -1, x will be equal to -2. So we're going to use those values that we have there. X being -1, x being -2. So we're going to use them here. Let me do this. We can use them, or there's this second method, but let's focus on the one which we can use them. So you can use this there, right, for you to simplify this. If, let's say, if I know some of you know this one, but you must know both methods. But the one here, this one is the first test which I used here. This one says that we are just going to simplify this side. So let's start by working on that one, then we'll come to the one of saying I'm going to use my x -1 -2. That one saves you, this one saves you time. So when I expand the first part, I'm going to get x squared plus 2x plus 1 inside here, right, which is this. Then when I expand this one, I get x squared plus 3x plus 2, which is this. Then when I expand, or the last one doesn't need expanding. Then this one plus this, right, is equal to this. So now let's start to simplify them. So I can take these two, they have a squared, right, equate them to 6. You say, right, I say a x squared plus, let me write the plus that side, plus b x squared, which will be equal to 6x squared. When I factor out x squared, the x squared will go. You say, right, I'll be left with a plus b, which is equal to 6. You say, right, this one's here, I should have written dots, not this dash. Remember, that is not a minus, that one is a dash, right? So the difference between a minus and a dash, check the size. So you should be able to differentiate that. So that one, the first one will be a plus b is equal to 6. The second one, I can take a 2x plus a plus b 3x, which is this. The x will go, right, if I equate it to 13. So I'm not going to take the coefficient. I'm just going to take this. I take a times 2, which is here, plus b times 3. Or you can simplify them in detail, right? It's also fine to simplify them so that when you take, you see which ones I'm taking, right? So I take a 2x plus 3b, then which is plus here, the one, this one also has x. I take plus c, then I equate it to 13. And then from now here, I can solve any of these, right? And then lastly, we take a, which when I multiply with this, we're gonna have a plus, this is 2b, which is this, then this is 2c, which is this. We equate it to 6, which is this, right? Then we can solve these anyhow. We can start from here. We make a subject the formula. When we make a subject the formula, we're going to get that a is equal to 6 minus b, right? So I can plug this anywhere. I can plug it here, plug it here, right? It's up to me how I want to do it. So when I plug it on the first one, let's say I do this. Let's find the n of this, right? We know that a is equal to so I'm just gonna plug it there so that we can see what we get. So if I plug a, we know that a is equal to 6 minus b. So if I plug a there, this will be 6 minus b. A will give us 12 minus 2b. When I take 2b plus 3b, I'm going to get this 12 to the other side. I'm going to get 1, right? If I take 12 to the other side, so I'm going to get that 1 is equal to minus 2b plus b. I'm going to get b plus c. So I get that b plus c is equal to 1, right? Then I make c subject the formula. C will be equal to 1 minus b. So we know that A is equal to 6 minus B, C is equal to 1 minus B. So I can come here and plug both of them. On A, I plug 6 minus B. On B, I leave it as it is because I don't have what is B, right? Then C, I plug 1 minus B, which this will be equal to 6. 6 to the other side, this will cancel out, right? So now this minus B plus 2B will give us B, plus this will be 2 minus 2B. So this will be, let's see, this is going to be, when you take this, this will be equal to 0. When I say 2, with this one is going to give us, it's what? It's B minus B. B minus 2B is going to be this, right? Then this will be minus 2. And then let's see if, oh yeah, B is supposed to be 4. Let me check if I didn't make a mistake when I was plugging. And this is supposed to be, let me write it in this way. I'm going to say, make sure that you pay attention, right? When I make a mistake, you show me that you made a mistake. So say that A is equal to what? 6 minus B, right? I'm going to write this, and we know that C will be equal to, when I plug here, A is 6 minus B, I'm going to get 12 minus 2B, right? And then plus 3B plus C equals to 13. Then we know that this is going to give us positive B plus C. When I take 12 to the other side, it's going to give us 1. And then here, I can make C substitute the formula to be 1 minus C, or minus B. Yeah, this is correct. 1 minus B. And then we say now, since we have A and we have B, so we can plug anywhere. This way we have A and C, right? So we can plug here and say that this is A, right? A is 6 minus B. So A is 6 minus B. And then I'm plugging on this one, right? And then plus 2B plus 2, or C will be 1 minus B, which is also 6. Then let's check this one. This will give us B. And then plus 2 minus 2B. Then 6 to the other side, it's going to cancel, right? Then this is going to give us B plus 2. Then this is going to give us minus B is equals to minus 2. Yeah, so it means that maybe, let me check, maybe I made vice versa when I was plugging this. Then it means that B is going to be 2, right? If I find here, now let's check A. What is A going to be? A is 6 minus B, right? So if I subtract 2 here, I'm going to get 4. Yeah? So it means that when I was putting this, I just opposed the right. So this is A equals to 4. Then let's check C. C is 1 minus B. So when I take this is going to be 1 minus 4. It's minus 3. So C is also minus 3. So it means that when I go back, our A, it's 4. So this is x plus 2. This was supposed to be 4. I just, when I was typing this, I opposed this 2. So it means that when I come to this, right, it means that this is supposed to be 4, 2. I'm just going to change these constants. 4, 2. And then our C is 3. So let's see how we integrate this. So how do we integrate? How do you know that the integral of this is ln? So if you let u be equal to this denominator, and let u be equal to x plus 2. When I derive this, I'm going to get dx, because that is the derivative of x plus 2 is going to give us 1, right, plus 0. So we have 1 times dx, we get that. And then when I come to plug there, I'll take the 2 outside, I'll be left with 1 over u du. Get dx is equal to du. Then this is going to give us ln u. And our u, we know that it's what? It's x plus 2. That's why I'm going to plug back the x plus 2. So you're going to do the same also for this one. You say, right? You make that u, then you derive that, and then you change it to this. You apply ln. Plus, but for this one, when you let this be u, check this. When you let this be u, you're going to be left with 3 minus 3 integral of 1 over u squared du. And we know that when we integrate this 1 over u squared, it's going to be in this format, u minus 2. So when I integrate this, I'm going to get u. If I add 1 on the numerator, I'll get minus 1, then divide by 1, plus c. Then this will be minus times minus will give us positive, right? Remember here there was minus 3. Then I'll also have minus 3. This will give us positive 3, 1 over u. So I can take this to the denominator as positive, right? Then when I plug back my x, my u man, u accurates x plus 1, I'll get this. You see, right, why it's in that format. Then we add our c. So now we see that this is not that difficult, right? So it's not difficult. It's that simple. So I think this is the last one, right? So what you can do, go through that part which I said that you must go through, right? So you must go through it. Maybe on the next session, if I come and ask questions based on that, and then you reply, it means that we're gonna finish it. So other than that, I think, guys, we can call it a day. All right.